and welcome to the last session of the blockchain course. Today, I'm going to tell you about a concept that is very central in modern blockchains, but we're not going to get too deep into it because it's more advanced than the level of this course. But it's nice to know the basics. And the concept is that of zero knowledge proofs. Okay. So what is it that we want? Basically, suppose that we have two different people. We have a prover and we have a verifier. And we usually just give them names that start with P and V. So the prover is usually called Penny, and the verifier is usually called Victor. Okay. And our goal is to design a protocol so that the prover can prove something to the verifier, of course. So, sorry, there's something wrong with my pen. Just a second. Position it here. Would it be better? Yeah. Okay. So our problem is that the prover wants to prove something to the verifier. Okay. Let's say Penny wants to prove, and whatever she wants to prove, I'm going to call it phi. I'm just going to give the statement a name to Victor. Now, this is usually proving that Penny knows something. So usually we talk about proofs of knowledge. So Penny wants to prove to Victor that, for example, she knows a secret key, or that she owns an account on Bitcoin, or things like that. But the really important point is that she does not want to leak any extra information. So without leaking any information other than phi itself. Okay. So for example, suppose I take the problem that we had in the homework. Suppose I'm Penny and I want to prove to you that I own 10 Bitcoins, but I don't want to give you any extra information. So I want to convince you that I own 10 Bitcoins, but I don't want you to know my public keys. I don't want you to know any information about which coins are mine. I basically don't want to leak anything. So this is what we call a zero knowledge proof. And we will see some examples of this, and we will see some non-examples, things that are actually not zero knowledge proofs. And hopefully by the end of this session, you will have a good understanding of what I mean when I say that something is zero knowledge. Okay, so let's start with a very simple example. Let's say that Victor is colorblind. Okay, so Victor cannot see color. And let's say that there are two identical balls of different colors. So let's say there are two balls and they are identical in everything except for their color. So let's say I have a red ball and then there is a green ball. Okay. Now Penny can see color. So she's claiming to Victor that she can distinguish between these two balls. So Penny's claim, or phi, is basically that she can distinguish between the balls. She can distinguish this ball and this one. Okay. Now, how can she prove this to Victor? If Victor cannot see color, how can Penny prove that she can see color? How can she prove to Victor that there is at least something, maybe it's not color, but there is something that she can use to distinguish between these two balls? Well, let me first give you a solution, and then I'll tell you why this is not a valid solution. So this is like my first non-solution. Here's the protocol. Let's say that Victor takes the balls and hides them behind his back. And every time he randomly picks one of the balls and shows it to Penny, and then Penny has to say what the color of the ball is. Okay, so basically my protocol is this. Victor chooses one ball uniformly at random and shows it to Penny. And then Penny says the color of the ball. Penny says green. Change. Penny says green or red. Okay. Now, of course, the interesting thing is that we have to repeat this. So we repeat this, let's say, n times. So for n iterations, every time Victor takes the balls behind his back, randomly chooses one of them, shows that one ball to Penny, and then Penny has to say green or red. Now, the idea here is that Victor can assign a number to the balls. In his mind, he can just remember which ball is number 1 and which ball is number 2. And whenever he shows the same ball to Penny, he just keeps track of whether Penny's answers are consistent or not. So if Penny always says green for ball number 1 and always says red for ball number 2, that means that, well, there is actually something that Penny can see. She can distinguish between the two balls, right? Now, why am I repeating this so many times? The reason I'm repeating it is because suppose the opposite is true. Suppose that Penny is lying. If she's lying and she cannot really distinguish between the balls, since every time I'm choosing one of the balls uniformly at random, she has only a 50% chance of guessing correctly. So if I repeat this n times, the probability that all of her guesses are correct goes down exponentially, right? So it's like 1/2 to the power of n. So if I repeat this enough times, it should eventually convince Victor with very high probability that Penny is not lying and she can actually distinguish between the two balls. Okay. So this is a proof protocol because it's a way for Penny to prove to Victor that she knows the color of the balls, or that she at least can tell the difference between the two balls. But the problem is that this also leaks some information. What is the information that is being leaked here? The color of the balls, right? So when Penny says green or red, this is an information leak. Because before the protocol, Victor didn't know the color of the balls. Remember, he's colorblind. But now, let's say he knows that ball number 1 is green and ball number 2 is red. That's some information. He has learned something that he didn't know beforehand. But we said that we want to have a zero knowledge solution, a zero knowledge proof. Basically, we don't want to leak any information. The only thing that Victor should find out is that Penny is telling the truth, that she can distinguish between these two balls. We don't want to leak any other information. This is very important. I'm not saying we don't want to leak useful information. I'm saying we don't want to leak any information. Okay. Now, how can I fix this? So let's do a fixed protocol. Basically, Penny shouldn't say the colors. But if she cannot say the colors, what can I do? Well, I can do a similar protocol, but every time when Victor shows the ball to Penny, Penny just says whether this is the same ball as last time or it's the different ball. It's the other ball. So I'm going to repeat this n times. Repeat n times. And again, you can choose n as you like so that you get whatever probability of confidence you want. And in every iteration, again, Victor chooses a ball uniformly at random. And shows it to Penny. And now Penny should just say whether this is the same ball as the previous iteration or it's the other ball. Penny just says same or changed, let's say. Okay. Now, let's see if this protocol can actually prove to Victor that Penny can distinguish between the two balls. And let's see if it leaks any information. Well, first of all, if Penny can distinguish between the balls, she can definitely answer correctly every time, right? Because she can see the color, she can see whether it's the same ball as the last iteration, so she knows whether it's the same or it's the other. So that part is fine. Now, let's say that Penny is a liar and she doesn't actually know the difference between the balls. Let's say she's also colorblind and the balls look the same to her. Because Victor is choosing the ball uniformly at random every time, Penny's chance of guessing correctly is 50%, right? But I'm repeating this n times. So the probability that Penny guesses correctly every time is actually 1 over 2 to the power of n. To be more clear, to be more exact, it's 1 over 2 to the power of n minus 1, because like in the first iteration, of course, it doesn't really matter what she says, because these answers only make sense from the second iteration onwards. Okay, but the probability goes down exponentially that she can actually cheat successfully. So if I have a huge n, in practice, if I set, let's say, n to 100, I should be pretty convinced by the end of it that Penny actually knows what she's talking about and she can actually distinguish between the two balls. And remember, this is exactly the claim that she wanted to prove. She wanted to prove that she can distinguish between the two balls. But now, does this protocol leak any information? You see, in the previous protocol, it was easy to just point out the information and say, this is what's being leaked, so this is not a zero-knowledge protocol. But I want to prove that this one is a zero-knowledge protocol. If that's the case, I have to prove that it doesn't leak any information. But how do I prove that? Well, the way I prove this is by saying that whatever Penny is telling Victor is something that Victor already knew. Okay? So if Victor already knows something and I say the same thing to him, of course, I'm not leaking any information. He already knows it, right? And if you look here, so Victor is the one choosing the balls every time. So every time when he takes the balls behind his back and chooses one of them and shows it to Penny, he knows whether it's the same ball or it's the other ball. So when Penny answers same or changed, this is an answer that Victor already knew. So Victor is not gaining any new knowledge. The only thing that he's finding out here is that Penny can distinguish between these two balls. Okay, so this is an example of a valid zero-knowledge protocol. Because we proved the statements that we wanted to prove, we proved that we can distinguish between the two balls, but we didn't leak any extra information. Okay. Now, let me give you another example. And this is also an example that is very classical. People usually use this example to just define the concept of zero-knowledge proofs for the first time. And here's the example. Suppose that there is a cave, and this cave looks like this. So let me see how I can draw this. Let's say I have something like this. And then so this is how the cave looks like. And let's say that there is some sort of a barrier or a door here. And this door has a password. So it's a cave. You can pass through this door only if you know the password. And now my second problem here, or the second example, is that Penny claims she knows the password. Okay. And let's just give names to these corridors. So let me call this one corridor A, and let me call this one B. Okay. And so Penny wants to prove to Victor that she knows the password. And let's say that both Penny and Victor are standing here. This is Penny, this is Victor. Now, what is a simple way of proving to Victor that she knows the password? Well, she can just tell Victor the password, and then Victor can go into the cave, go through A, reach the door, use the password to pass, and come out of B. And Victor would know that the password was correct, and Penny actually knew the password, because of course he could pass through the door. But of course, this is the farthest thing from a zero knowledge proof, because you're literally leaking the password. And the whole point is that Penny wants to prove to Victor that she knows the password, but she doesn't want Victor to gain any extra information. Okay. What else can we do? Well, here's the other thing that we can do. And this is also an example of something that is not zero knowledge. So we can ask Victor to just stand here. So this is where Victor stands, and he can see what's going on. And then Penny can go in, and she can go into A. So she can go like this, and she can go here, tell the password, and pass through and come out of B. Okay. So the thing that Victor is going to observe here is that Penny entered from A but exited from B. And this would prove to Victor that Penny knows the password. Okay. But my question is this a zero knowledge proof? Is this a ZKP or a zero knowledge proof? Because you see, this time Penny is not telling Victor the password. She's just going here and using the password herself. And let's assume that this is such a long cave that when she's using the password here, Victor has no way of observing that. So the only thing that Victor is observing is that Penny went through A and came out of B. Okay. Now, here's the thing. Even this is not a zero knowledge proof, because our concept of information leak is actually very strict. When we talk about protocols, we're usually talking about protocols that will somehow be implemented on the blockchain or be implemented on a network and so on. Of course, here I'm just using a physical example. But in all of the cases where you have a network or blockchain or so on, whenever some party sees something, they can also record it, right? So if I reach some state in the blockchain, if I see some transactions, if I have the state of a smart contract, of course, I can keep a record of it. Even without a blockchain, if I'm on a network and people are sending messages, I can just keep a copy of all the messages that I have received or seen, right? So part of our assumption is that whenever Penny is proving something to Victor, Victor can record everything that he sees. He can record his point of view of the interaction. So in this case, the metaphor is that Victor has a video camera and he can record what's happening here. He can record that Penny has entered from A and came out of B. Now, why is this leaking any information? Because Victor can now take this recording and play it for someone else. And it would prove to that someone else that Penny knows the password as well. Okay, so this is the information that is being leaked here. So I say that Victor records Penny's entrance and exit. And let's say that later on, Victor meets someone else. So let's say Victor plays this recording later on for, let's say, Alice. Okay. Now, when Victor plays the recording for Alice, this convinces Alice that Penny knows the password. This convinces Alice that Penny knows the password. Now, why is this a problem? Why is this a leak of information to Victor? Because before the interaction with Penny, Victor couldn't convince Alice. So if before seeing this interaction, Victor went to Alice and tried to prove to Alice that Penny knows the password, there was no way for Victor to do this, right? But now, after this interaction with Penny, Victor has this extra ability. He has the ability to convince someone else, to convince Alice that Penny knows the password. And the fact that Victor gains some new ability means that he has some new knowledge. And that's a leak of information. It's a very subtle kind of knowledge, but we don't want to allow even that. We want to make sure that Victor is only convinced himself that Penny knows the password, but we don't want Victor to be able to convince anyone else. Generally speaking, if I want to formalize this further, which we don't really do this in this course, but the formal definition is that Victor should not be able to compute anything that he couldn't compute before the interaction. That's the definition of not having any new knowledge. So you have new knowledge if you can do something that you couldn't do before this zero knowledge protocol. Okay. Now, how can we actually do a zero knowledge protocol here? Well, here's what we can do. We can say that Victor stands here. This is where Victor is. And let's say that from here, he cannot see the entrances. And then Penny goes in. Penny goes in and she chooses one of the two entrances to go to the door. So maybe Penny chooses entrance A and ends up here. Or maybe she chooses entrance B and ends up here. And then Victor enters the cave and comes here. And then he randomly chooses A or B, and he just shouts A or B. Penny hears what Victor has chosen, and Penny comes out of the corridor that was chosen by Victor. So if Victor chooses B in this case, Penny will just walk back. If Victor chooses A, Penny will use the password to pass through the door and come out of A. Okay? Now, again, we can do an analysis like before. If Penny is not lying, if Penny actually knows the password, then she can definitely always come out of the corridor that was chosen by Victor. So she will succeed with probability 1. She will succeed all the time. But if she's lying, since Victor is choosing the corridor uniformly at random, there is only a 50% chance that Penny happened to be on the right side. And if she doesn't know the password and she's on the wrong side, she cannot come out of the chosen corridor. So if Penny is lying, she only has a 50% chance of succeeding. Now, 50% is a lot, but just like before, I can just repeat this protocol n times. So we just keep doing this over and over again. Every time that Penny is successful, we reset the protocol. And again, Penny chooses one of the entrances, goes in, then Victor comes in and chooses one of the exits uniformly at random, and Penny has to exit from what Victor chose. And this reduces the probability that Penny would succeed in all of the iterations exponentially. It's like 1 over 2 to the power of n. Okay, so this would convince Victor that Penny is not lying. But is this protocol a zero knowledge protocol? So does Victor gain any new understanding? Does Victor get any new knowledge? Now, again, the problem here is that we have to argue about whether we told Victor something that he didn't know. Now, you can do that argument like the previous case, but there is also another way of doing this. And this other way is based on this idea of a recording. So suppose that I did this protocol, and let's say that Victor again had his video recorder and he recorded everything that happened in this protocol. Okay. And now he goes and shows this recording to someone else, shows this recording to Alice, let's say. imagine that you're Alice and I'm Victor and I'm showing you a recording of this protocol. I show you a video that basically contains only my part of the protocol, what I saw in the protocol. So it shows you that Penny goes in, and it shows you that I go in and I randomly choose one of these two exits, and Penny exits from the correct corridor. And let's say that I have a recording of all the n iterations, and it shows that in every iteration, Penny came out of the right corridor. Would you be convinced that Penny actually knows the password? You see, of course, the protocol was convincing to Victor, but if he takes a recording of this protocol and plays it for someone else, would it convince them? And the answer is no. Because if you're Alice and if you're seeing a recording of this protocol, it's like the recordings of magic tricks that you can see on YouTube. It's never something that would convince you. Why? Because maybe Victor and Penny were actually colluding with each other and they were just faking this. You have no way of knowing. And this is how I can actually prove that a protocol is a zero-knowledge protocol. I can say that if Victor, if the verifier records every interaction and then later plays this for someone else, they would just think that the whole thing is fake. They would think that, well, Victor could just make this recording on his own. Now, of course, again, these are examples of zero-knowledge proofs that use some physical phenomena, but in practice, we're using zero-knowledge proofs in smart contracts and on the blockchain and so on. So this gives you a way of actually proving something to someone without leaking any information. And also, this includes without leaking the ability for them to replay this proof for someone else. So Penny can convince Victor, but Victor not only cannot do anything new with this information, I mean, he's convinced that Penny knows the password, but he cannot compute anything that he couldn't compute before. So he cannot even convince someone else that Penny knows the password. Okay. So let me give you some more involved examples of zero-knowledge proofs. And these are things that, well, they're not really modern zero-knowledge proofs. These are like the classical examples. All of them are at least 20 years old. But the modern ones are too complicated for this course. So here's an example that is actually based on Diffie-Hellman or based on El-Gamal. So I want to do this. Let's say that I have a big prime number P, and let's say that everyone knows P. So everyone knows P, and this P is a huge prime number. And let's say that everyone also knows a number G, which is a primitive root modulo P. Okay, and let's say that everyone also knows a number X, and this X is just some number between 0 and P minus 1. Okay, now when we were talking about El-Gamal, we said that computing discrete logarithms is actually a hard problem. It's a problem for which we don't have a solution. So if I know X, it's really hard to find log of X. But now, suppose that Penny claims that she knows it. So Penny claims she knows a value of Y. So she knows some Y, and this Y is, of course, a secret, such that if I look at G to the power of Y, that's equal to X or congruent to X modulo P. Okay. And she wants to prove this to Victor. So basically, she wants to prove that she knows the log of X in base G. But this is not a normal log, this is discrete log. So all of our calculations are modulo P. She wants to prove that she knows a value of Y such that G to the power of Y is congruent to X modulo P. Okay. How can we do this? Well, if you remember El-Gamal, In El Gamal, basically, we had a similar situation, but Y would be the secret key of Penny, and X would be her public key. So basically, what Penny wants to prove is that she owns the secret key corresponding to a particular public key, right? So everyone knows the public key X. Penny wants to prove that she knows the secret key Y that corresponds to X. How can she prove this? I mean, it doesn't even have to be El Gamal in particular. You can use any kind of encryption here. If I want to prove that I have the secret key, I can do it by just telling you to send me a message. So Victor can just send a message to Penny, and let's say that this is an encrypted message, and then Penny has to decrypt the message and send the decrypted version back to Victor. And if she can successfully decrypt it, then Victor is convinced that she actually knows the secret key. Okay, so this is basically using El Gamal. So this is my first protocol. Basically, it's the same as El Gamal encryption. And it's like this. So Penny, let me just draw these things. So let's say this is all the information that Penny has, and this is all the information that Victor has. I did it with a C, right? Okay. Now, what does Penny know? Penny knows a value of Y, and this is a value of Y such that G to the power of Y is X. Okay. Now, what can Victor do? We said that we want Victor to send an encrypted message to Penny. Now, remember that El Gamal was basically like an offline version of Diffie-Hellman. So the way this works is that Victor also uses some value. Let's say Victor randomly chooses some Y prime. And let's say that G to the power of Y prime is X prime. Okay. And now remember how Diffie-Hellman key exchange worked. So you have X, which is public, and Victor can compute X to the power of Y prime. But also, anyone who has X prime and Y can calculate X to the power of Y prime, which is the same as X prime to the power of Y, right? So Victor is going to also choose a random message, let's call it M. So both Y prime and M were chosen randomly. And now he's going to send this message to Penny. He's going to send X prime, and he's going to also send M plus X to the power of Y prime. Okay, now he can calculate all of these things. So X prime is public, that's fine, he knows it. And of course, he knew Y prime, so he could compute X prime in the first place. M is the random message that he has chosen. And X was again public. Remember, X is just G to the power of Y, and we said that that's public. And Y prime was Victor's secret, so of course Victor can compute X to the power of Y prime. So he sends this message. And now let's look at this from the point of view of Penny. This is basically the same problem as in Diffie-Hellman key exchange. So if I look at X to the power of Y prime, what is X to the power of Y prime? So X was G to the power of Y. So X to the power of Y prime is G to the power of Y prime. But this is the same as X prime to the power of Y, because X prime was G to the power of Y prime, which is. So when Victor sends X prime to Penny, Penny can compute X prime to the power of Y because she knows Y, which means that she can compute X to the power of Y prime, and she can subtract it, and she can find the message. So she does that, and she basically makes the message public. She sends the message M back to Victor. Okay. All I'm doing here is El Gamal encryption and decryption. So Victor took the message M, encrypted it using El Gamal, sent it to Penny. Penny decrypts it and sends the decrypted version back to Victor. And because only someone who knows the private key can do decryption, assuming that El-Gamal is a safe encryption, this proves that Penny actually knew the secret key. So with just this protocol, Penny proved to Victor that she knows the value of y such that g to the power of y is x. Now, is this a zero-knowledge protocol? Well, kind of. It's a zero-knowledge protocol under some assumptions. What is the assumption? The assumption is that El-Gamal encryption is secure. But we've talked about this on the lecture on El-Gamal. We pretty much believe that it is. Okay, so assuming that El-Gamal encryption works correctly and it's a secure way of encrypting, this is a valid zero-knowledge proof. And it proves exactly what we want. It proves that Penny knows a y such that g to the power of y is x. And it's a zero-knowledge proof for the same reason as before. Let's say that Victor is recording the whole interaction. So he records the message that he has sent to Penny, and he records the message that Penny has sent back. And let's say that all of these messages also have signatures on them, so you cannot forge them. And let's say that Victor takes this recording and brings it to someone else, brings it to Alice, and shows it to Alice. Alice would just not be convinced. Alice would claim that, well, you were colluding with Penny, or maybe Penny doesn't even exist. Maybe Penny is just simulated by Victor. Because the whole point here is that when Penny announces M, because only Victor knew M, this is convincing to Victor because he now knows that Penny could somehow decrypt the message. But if I want to show this to a third party, why would this be convincing to them? Maybe you have already leaked the message, or maybe Penny is just the same as Victor. Maybe you've just created a fake video, a fake transcript of the protocol. Okay? And because I cannot convince a third party of anything, that basically means that any information that I'm getting in this protocol could be something that I could compute on my own, that I could fake on my own. So I'm not getting any new information. So this is a zero-knowledge protocol. Victor has no new information. Okay. Let me give you another example. And this is actually an example which is very interesting. Let's do the example of tree coloring. So tree coloring is an NP-hard problem. It's actually also NP-complete. And basically, the problem is that you have a graph and you want to assign one of three colors to each one of the vertices. And then you want to make sure that no two vertices that are connected to each other have the same color. Okay, so this is my situation. Let's say we have a huge graph. We have a graph G. And I'm going to assume that this is a really big graph. This is huge. Because if G is small, then tree coloring can actually be solved, right? So I can just brute force and try all the possible colorings, for example. And then let's say that Penny claims that she knows a tree coloring of G. So she wants to prove this to Victor. Let's say I have my graph. Let's say this is my graph. Now, again, in reality, this graph will have millions of vertices. Otherwise, it doesn't really make it that convincing. And let's say that I know a way of coloring this graph with three colors. So I'm doing this one blue. I'm saying this is red. This is green. This has to be blue now. And let's say this is red. This is again blue. And this is green. Okay. So I know how to color the vertices with three colors such that no edge has the same color on both of its endpoints. So this is what Penny is claiming. She wants to prove this to Victor. She wants to prove to Victor that she knows the tree coloring. But again, we want to give a zero knowledge proof. We want to make sure that Victor is just convinced that Penny knows the tree coloring, but he finds no extra information. And again, the definition of no extra information is that he cannot compute anything new. He cannot compute anything that he couldn't have computed before this protocol. Okay. Now, how can I do this? Well, actually, I'm going to use a hash function, and I'm going to use kind of a commitment scheme. So this is the first step. I say that in step 1, Penny just chooses a coloring of G. Okay, Penny chooses a coloring of the graph. Now, here's the question. How many different colorings does Penny know? I know that she knows 1 3 coloring, right? But if you know 1 coloring, you can just apply any permutation to the colors, right? So if you have one way of coloring the graph with 3 colors, you actually know 6 ways of doing it, assuming that R3 of your colors are used. It's actually pretty easy to check if a graph is 2-colorable. That's the same as saying that the graph is bipartite. So we are assuming that this graph is not bipartite. We are assuming that we need at least 3 colors, but Penny's claim is that she knows a way of doing it with exactly 3 colors. So if she knows 1 coloring of this graph, she actually knows at least 6 different colorings, right? Because 3 factorial is 6, and I can just permutate the colors. So I can, for example, say, change all the greens to blue, all the blues to red, all the reds to green. Okay. So when I say Penny chooses a coloring, basically what I mean is that she knows at least 6 colorings. Let's say she knows exactly 6 colorings and chooses one of them uniformly at random. If she knows more than 6 colorings, good for her. I don't really need that part. I can just say, take these 6 colorings that are all obtained from basically permutating the colors in 1 coloring and choose one of them uniformly at random. Okay. And then I want Penny to commit to this coloring. So this is step 2. Penny commits to the coloring. Now we're going to use a hash function for the commitments. And basically, this is what I'm going to do. I'm going to say for every vertex I, which has some color, let's say of color Ci, Penny chooses a nonce, chooses some nonce Ni, and announces the hash. So she announces Hi, which is the hash of I, Ci, and Ni. Okay, so she just gives all of these hashes to Victor. For every vertex, she's sending 1 hash to Victor. Now, of course, this is like a commitment scheme. As soon as she sends all of these hashes to Victor, this means that she has committed to the coloring. She can no longer change the color, right? But at the same time, Victor doesn't know any of the colors. Okay. But Victor wants to make sure that this is a valid coloring. Victor wants to make sure that no 2 neighboring vertices have the same color. Now, he cannot ask about all of the edges, because if he asks about all of the edges, he will eventually find out the coloring and it would leak information. But we say that he can ask about 1 particular edge, and he gets to choose that uniformly at random. So in step 3, I say that Victor chooses 1 edge of the graph. So let's say the edge is E, and it was an edge between vertices U and V. And let's say that he chooses this uniformly at random. Okay. And then in step 4, we have a reveal. But the way this works is that Penny only reveals the hashes corresponding to these 2 vertices. So Penny reveals the color of U, the color of V, and the nonces that she used for U and V. And of course, finally, Victor checks that Penny was not cheating. So Victor checks that the hash that Penny told him for U is actually the hash of U, color of U, N of U. So he checks that this was not a lie. And he also checks that the hash that Penny gave him for V is the hash of V, color of V, nonce of V. Okay. And very importantly, he also checks that the color of U is not the same as the color of V, because U and V were the two endpoints of an edge that Victor chose randomly. And of course, they shouldn't have the same color. Okay, this is my protocol. Now, of course, just as before, I would repeat this many times. So I would say repeat, let's say K times, and we will come back and talk about how many times is enough. But let's see what happens here. Well, first of all, if Victor sees that Penny is cheating, if Victor sees that the hashes don't match, or that the same color was assigned to the two neighboring vertices, Victor would definitely reject and would say, well, I don't believe you at all. So let's just look at it from the point of view of Penny. And let's see what is the probability that Penny can go through this protocol successfully if she actually knows a tree coloring of the graph, and what is the probability that she's successful if she doesn't know a tree coloring of the graph. Okay. So first, let's say that she does know a tree coloring of the graph. Let's say she knows, for example, this coloring. Because she knows this coloring, of course, she can just choose any of the permutations of this coloring. So she can choose one of the 6 colorings uniformly at random. She can make all of these commitments. That's fine, because for every vertex, I know the color, and I'm choosing a nonce is not hard. Running a hash is not hard. I'm just going to compute all of these HIs and give them. And then when Victor chooses an edge, fine. Penny can reveal the colors of the 2 vertices at the 2 endpoints of the edge. So of course, if Penny knows a tree coloring, she can successfully prove this to Victor. So she can run this protocol successfully, and all of the Victor's checks at the end pass. Okay, that's fine. But what if Penny doesn't know a tree coloring? What if she's lying? What if her claim doesn't actually hold? So because she doesn't know a tree coloring, she has to fake it. And in step 1, she cannot choose a coloring of G that is actually valid, right? She cannot choose a coloring that assigns different colors to the endpoints of every edge, because if she could do that, she already knew a tree coloring. I'm assuming that she doesn't know a tree coloring. Okay, but then she's just going to choose a fake or invalid coloring, and she's going to commit to it. And there is no way to really cheat in the commitments, because she's giving these hashes, and then in the end, the hash is verified. So I'm not assuming that she's cheating here. What she's counting on is that maybe when Victor chooses one edge, it just happens that Penny is lucky, and these are 2 edges and 2 vertices that have different colors. Okay, so let's say, for example, I have this same graph. So let me just draw this again. Okay. And let's say that Penny doesn't actually know a tree coloring. So what she knows, or what she has faked, is something like this. It's an invalid coloring. Okay. And this is invalid because there are 2 red vertices that are actually neighbors. Okay. But she has used this invalid coloring, and she has committed to it. And the idea is that, well, Victor is just going to ask me about a random edge. So maybe I'm lucky, and Victor asks me about an edge that has 2 different colors on its 2 endpoints. But because I don't have a valid coloring, I am sure that there is at least one edge that would be unlucky for Penny, right? There is one edge that has the same color on both endpoints. So here, Victor is choosing the edges uniformly at random. So there is at least a 1 over m probability, where m is the number of edges, that he chooses this bad edge that had the same color on both endpoints. And if that happens, because Penny cannot change her commitments because she has already committed to the colors, she would be caught, right? She would have to reveal. Of course, if she doesn't reveal, she loses because Victor would just reject. And if she reveals, Victor would see that the colors on the two endpoints are the same. So basically, if I want to summarize this, if Penny is honest, if Penny knows a tree coloring, she always succeeds. Okay. If not, if she doesn't know, then her probability of failure is 1 over m at least. So she succeeds with probability at most m minus 1 over m. And remember that m was the number of edges. Okay. Now, this is a huge probability, right? So imagine if I have 1,000,000 edges. Of course, just saying that the probability of success is 999,999 over 1,000,000. That's a huge probability. So it seems like she wouldn't be caught. But again, we go back to this point. I'm going to repeat this k times. And Victor is going to accept the proof only if Penny is successful every time. So if I repeat this n times, the probability that she succeeds, sorry, if I repeat this k times, the probability that she succeeds in all of them, so probability of success in all k iterations, assuming that she doesn't know it's recoloring, is actually at most m minus 1 over m to the power of k. But you get to choose this k, and m minus 1 over m is less than 1. So you just choose this k so that m minus 1 over m to the power of k is a very small number. And this would prove with very high probability to Victor that Penny actually knows a tree coloring, and that's why she's succeeding in the protocol. Now, why is this zero knowledge? So first of all, I want you to realize that every iteration of this protocol, every repetition of this protocol is completely independent of the previous repetitions, because every time Penny is choosing a coloring and she's choosing it randomly, right? So whatever information you had from the last iteration isn't really helping you in the current iteration. And the other thing is that even though Penny is committing to all of the colors, she's only revealing the colors at two vertices that were connected to each other. So she's only revealing the color of the vertex U and the vertex V. But let's just look at two vertices. Let's say this is vertex U and this is vertex V. What are these colors that Penny is going to reveal? We said that Penny is going to choose one of the 6 colorings uniformly at random. And there are actually 6 different ways of coloring U and V, right? So I can have blue here, and then I can have green or red here. And generally, for any color that I assign to U, I have 2 choices for the color that I assign to V. But Penny is choosing one of the 6 colorings uniformly at random, so she's choosing one of the 6 assignments of colors to U and V uniformly at random. Which basically means that the information that is released to Victor here, the color of U and color of V, this is random information. This is just something that was chosen in step 1 by Penny uniformly at random. So it's not really leaking anything to Victor that would allow him to compute anything new. So this is a zero knowledge protocol. Okay, so that's it for this course. I'll see you at the final exam. Have fun.